Excited to be here, and thanks to the organizers for giving me this chance. So I've been, for a long time, interested in how animals learn associations in their world. And over the last 7 years, my favorite animal has been this particular human shown here, who, believe it or not, actually does have a body, as you can see in this more updated photo. So the story goes that when she was 2, my daughter had an incredibly life-altering experience. It was easily the most meaningful thing that had ever happened to her, and that's this. And ever since then, she's been able to recognize that this particular cue means the world's best ice cream, right? So the question that I'm interested in is, how did she learn this cue-reward association? And as neuroscientists, we have generally believed that this question is solved and that we understand exactly how this is happening. And the idea is what I'll refer to as Model 1 here. So the idea is that, like, my daughter would predict the outcome of the cue, and whenever there's a prediction error, then she would use that prediction error to update the prediction and form a better prediction, right? So the idea is that this is a trial and error sort of learning, where you would try out a prediction, and if there's an error, you would actually learn from the error. And there's a lot going for this model. As I said, this is sort of considered as, like, essentially ground truth in some sense in the field of neuroscience. So one of the big things that is going for this model is that if you look at the activity of midbrain dopamine neurons and also look at the release of dopamine in downstream targets, you find that their activity is very compellingly consistent with the signaling of a reward prediction error signal. But because this is all pretty well established, I'm not going to go in detail about this part. So recently, as sort of James said, we've sort of provided one possible alternative model for how animals could be learning associations in their world, and also possible models for a possible alternative for what dopamine might be doing in such learning. And this was work led by a really talented postdoc, Hee-Jung Jung, in my lab. Because this is published now, I'm not going to go into detail about the work, but I'll just give you a brief overview of it. So the idea is, at a big picture level, that instead of learning predictions directly through prediction errors, my daughter could have learned retrodictions, if you will. So what that means is she would simply store events in memory as they happen, but when something very meaningful, like an ice cream, happens, then she would look back in her memory to identify what might have caused it, right? So she would learn this association by looking backwards from meaningful effects to identify the causes, right? And to give a bit more intuition about this, imagine that you are sick one day, and imagine also that you happen to eat at a new restaurant earlier that day. So I bet you that you would associate eating at that restaurant with the feeling of getting sick. And I'd also bet you that the way that you would do that is by getting sick and then looking back in memory to identify what might have caused this, right? And it is explicitly this retrospective look-back process that's the essence of our theory. So from this example, you can see 2 core principles of the account. So one is that even though you've learned this association between the restaurant and the feeling of getting sick, by looking backwards in time, you can implicitly convert that to a prediction, right? Because the next time you see that restaurant, you can predict that if you ate there, you might get sick. So the first core principle is that one can predict the future by retrodicting the past. The second core principle is that you don't really want to be retrodicting at all possible times. You only want to be doing this when meaningful things happen, right? Like ice cream. And so the second core principle is one retrodicts the past only after meaningful events. And the idea for us for dopamine is that dopamine actually conveys that the event that just happened is meaningful enough that you should be looking back and try to identify its cause. But I'm not going to talk too much about the dopamine part here. I'll just formalize the first principle. So how do we formalize the first core principle that one can predict the future by retrodicting the past? So it turns out that Bayes' rule actually does this for us. And this is a little bit of abusive notation, especially for this crowd, but I've simplified things here. So what I'm showing you here is that the probability that the reward follows a cue, so conditional on the cue, what is the probability that the reward will come after that, is equal to the probability that the cue precedes the reward. So conditional on the reward, if you look back, does the cue precede it, times an overall probability of reward divided by overall probability of cue, right? Now here, the only associative quantities, the quantities that measure the association between the cue and reward, are either this or this. And this here is a prediction, because it is the prediction that the cue is followed by reward, whereas this here is a retrodiction, because it is the probability that the cue precedes a reward, right? And this is not an associative quantity, it's just the overall probability of reward, overall probability of Q. So our hypothesis was that if animals learn and store this as actually the memory or the association between the cue and the reward, then whenever they need the prediction to guide their behavior, they can use Bayes' rule to compute that on the fly in real time, right? So the idea was that animals, the simplest idea is that animals are actually learning to store this, and this is what is stored in memory. And for the aficionados in the audience, this also works for successor and predecessor representations, but I'm not going to get into that here. So I know that I don't have to apologize for showing a math equation here, but nevertheless, so to set up the question of why am I showing you this equation? The reason I'm showing you this equation is that it has some really wacky implications for learning, and so the rest of the talk is just going to be focused on that. So to look at the first one, I'll talk about work led by another really talented postdoc, Dennis Burke, in my lab. So to set this up, let's imagine a thought experiment. So in this thought experiment, we have two groups of animals, let's say mice, because you'll see mice very soon, that are both learning the association between an auditory tone and a reward, right? So the idea is that this tone here is followed at a very short delay with the reward. So let's say that this gap here is just 1 second, right? So that's the same for both of these groups, for all these pairings. The only difference between the groups here is that this gap from the reward to the next cue is about 1 minute for this group. So it's obviously not drawn to scale because this tiny gap is supposed to be a minute. Well, this gap here, which almost looks the same, is a second, right? So the difference is that here, this gap is 1 minute. So that means over 10 minutes, this group gets 10 pairings of the cue and reward. While for this group, this gap is 10 minutes. So over 10 minutes, they get 1 pairing of the cue and reward. So the question in the thought experiment is, give both of these groups of animals the same total duration of experience in the task, let's say 1 hour, such that this group gets 60 pairings, while this group gets 6 pairings. The question is, which group will learn more about the cue-reward association, right? And the answer should seem blindingly obvious. The group that gets literally 10 times more evidence that the cue and reward are associated should learn more about the cue-reward association, right? And that's by and large consistent with the framework of Model 1 that I proposed, which is not a single model, it's a family of models. Because in the end, trial and error learning is about repetitions, right? So to break this down a little bit more, if we imagine a plot between the total time in the task until the animals show any evidence of learning, and you plot that against the time that the animals are spending per trial, then you would imagine that if the number of trials that it takes them to learn the task is fixed, right? So if the animals learn in like 50 trials or something, then as you increase the time per trial, you would increase the total time until learning, right? Because that's just the product of the number of trials it takes times the time per trial, right? So if you imagine a plot between these, in the extreme case where the animals learn in a fixed number of trials, regardless of how much time they spend per trial, you'll get a straight line where the slope is just a fixed number of trials. So this is obviously consistent with Model 1, but it's not the only regime that is consistent with Model 1. You can also have scenarios that live sort of below the space that are broadly referred to as reflecting the trial spacing effect, where the idea is that as you increase the time per trial, the animals will take fewer trials to learn, but it's still such that the total time it takes them to learn is still going up. It's just not going up as much as you would go up here. Right, so both of these regimes are generally consistent with Model 1, and it depends on the parameters, et cetera, and the specific models and stuff. But the model that I just laid out, the Bayes rule stuff, I'll show you, will make a very different prediction, and that prediction is going to be that the curve here is a horizontal straight line, such that the learning is going to happen in a fixed total time, regardless of how much time you spend per trial. So what this means is that as the time per trial expands and increases, the number of trials it takes you to learn proportionally decreases, right? So that can be mathematically expressed as this. 1 over trials to learn is going to be proportional to the inter-reward interval, which inter-reward interval is the time that you're spending per trials here. And so that means that the product of these two things, which is the total time it takes them to learn, is going to be a constant. And so from this, you can see that if you have a learning rule where the learning rate per reward is proportional to the inter-reward interval, then you would actually lie on this horizontal straight line, right, in terms of time it takes to learn. So why am I saying that the previous model actually predicts this? To see this, let's go back to that equation, and I'll denote this as a retrodictive updates or retrospective updates. So if you think about when these updates actually happen, and you blow up a couple of these trials a bit more to scale, you realize that these updates are, by definition, only going to happen when you get the rewards, right? Because they're conditional on the rewards. So the frequency of these retrospective updates is going to be determined by the inter-reward interval, right? So the longer the inter-reward interval, the lower the frequency of the retrospective updates. On the other hand, the frequency of these updates, the overall probability of reward, overall probability of Q, can be much higher and continuous, right? And because this is just reflecting the overall reward rate and overall Q rate, right? It doesn't really depend on conditioning on any events. So from this, I'm going to make a postulate here. I'm going to make the postulate that if this base rule is supposed to be reasonable for a possibly dynamic world, then animals want to be calculating all of these quantities over the same amount of data in their past. Right? So what I mean by that is, imagine that they calculate this quantity over the last 1 hour of experience, where so over the last 1 hour experience, they look at every possible time that they got the reward, what is the probability that the Q precedes it? Then if this quantity reflects the last 1 hour of history, then I would also propose that these two quantities should also reflect the same 1 hour of history, because if the world changed during that time and you don't account for it, then you'll have like a mismatch here. And we can talk about that in detail if you want. So if we just assume that all the timescales here should be the same, then there's a problem. The problem is that the frequency of updates for both of these things are very different. And so the only way for the timescales to be the same is if something else holds, which is that the learning rate, the amount that you learn per reward, per retrospective update, should be proportional to the inter-reward interval. Essentially saying the learning per update times its frequency of updates should be constant for all the different things. And so from this, you can see that the learning rate is proportional to IRI, which I showed you in the previous slide, should actually imply that the learning will happen in a fixed total amount of time. So for these two examples, the inter-reward interval here is 10 times the inter-reward interval here. So that means a single reward should produce 10 times as much learning as a single reward here. And that essentially means that both groups should learn the same overall amount in the same total time. Said a different way, removing 9 out of 10 of these trials, thereby making this group equivalent to this group, should actually produce no deficit in the overall learning, right? So it should produce no change in learning. So from here on out, I'm going to show you actual data. So as I said, like this was tested in head-fixed mice, and the task that we used was exactly similar to the thought experiment. We had like a 250 millisecond short auditory tone, followed 1 second later by a reward. That trial period was identical for both groups. The only difference was one group had 1 minute ITI, the other group had 10-minute ITI. So it's exactly like the thought experiment. And so how do we measure learning here? The way we measure learning here is by looking at whether animals lick in anticipation of the upcoming reward. Right, so the animals don't have to lick in anticipation of the upcoming reward, but they nevertheless do. Initially, they only consume the reward, but after they learn, they start to lick before the reward, after the cue. Right? So it's in anticipation. And so if you look at the learning curves of basically on the averaging of the anticipatory licking across trials, you find that this curve seems to go up in about hundreds of trials, while on that same axis, this curve seems to go up much, much faster. Now, I often get the question of why do animals actually show anticipatory licking at all? Because it seems like a waste of energy. You just wait for the reward, right? So I'm not going to justify it properly, but I'll say that this is proof by cuteness in some sense. I'm going to show you that this also happens in humans. So this is a video of my daughter, and she's waiting in anticipation of the ice cream, which she knows is about to come. And you'll see anticipatory jumping behavior. And you'll also see that as the ice cream is nearing closer and closer, the vigorousness of the jumping increases higher and higher. Right? And obviously, this is a waste of energy. She didn't have to do it, but she's obviously excited, so she's still doing it. So that's what I think is also going on in the mice. So as I said here, the learning curves seem to be operating on different scales here, right? Like on the same axis. So now what would happen if we plot these learning curves as a function of time in the task, such that the trial numbers are scaled by a factor of 10, right? So now you see that the learning curves completely overlap. So that means that a single reward for this, or a single trial here, was literally worth 10 trials for the other group in terms of learning, right? So the learning curves completely overlap here. And this also happens to be true not just at the behavior level, but also at the level of the emergence of the dopamine response to the cue that predicts the reward. But I'm not going to talk too much about this here. Okay, so next we checked whether this is just somehow magically a consequence of the 1-minute ITI and the 10-minute ITIs that we used. So to check that, what we used was half a minute ITI and 5 minutes ITI. And then when we do that, we find this exact same scaling between these two groups of mice. But now when we plot all 4 of these groups of mice, so the half minute, 1 minute, 5 minutes, and 10 minutes, all on the same curve with time being on the x-axis, you find that all the learning curves completely overlap, right? So that means for this group, every reward that they experience is equivalent to 20 rewards that this group gets. But nevertheless, the total amount of learning is still the same. So just to pictorially show roughly what the task looks like for these groups, it looks like this. So they're spaced apart like really a lot, but nevertheless, the time that it takes them to learn the task is the same, exactly like I set up with that horizontal line on the schematic, right? So this shows that the number of trials is really not the key determinant here. It's a total time that seems to be the determinant of overall learning. Now, the wackiest implication of this learning proportional to IRI happens in partial reinforcement. So let's imagine now that we have a different group of animals where they're actually learning that the cue predicts the reward only 50% of the time, right? And I'm going to use the 1-minute inter-trial interval. So if the cue predicts the reward only 50% of the time, the inter-reward interval is going to be doubled because the rewards are twice as sparse. So that means that our learning, where the learning rate was supposed to be proportional to the IRI, should predict that the animals would learn twice as fast in terms of number of rewards. So they will actually learn in half the number of rewards, even though you weaken the association, right? And that is actually true. So if you actually look at the number of rewards it takes them to learn the behavior, it is exactly a half of what it takes them to learn with the 100% probability. But once they learn the task, the amount of reward-seeking behavior, or the amount of anticipatory jumping, like what my daughter was doing, is reduced, right? So the amount of behavior performance is actually proportional to the reduction in the association, but the learning itself is inversely proportional. Now, one thing that's really interesting that happens here is that you can have some animals that never show evidence of learning in this task. So those are these non-learners here, those are shown in the black curves. So the solid black curve is the cumulative sum of the total behavior. And you can see that this is basically lying on 0, right? So that means they're not showing any behavioral evidence of learning. But interestingly, this dotted line, or the dashed line, is actually their underlying cue response to the dopamine release, right? And you can see that even though these animals show no behavioral evidence of learning, they show completely intact neural learning as far as dopamine is concerned. In fact, in a way that is just indistinguishable from the animals that actually show behavioral learning. So there's clearly dopaminergic learning that's going on in their heads. It's just not getting translated to behavior. So then we figured that we could use this fact, that the dopamine learning is actually a lot more sensitive measure of learning, to actually test an even wackier implication of this, which is that if you actually reduce the probability now all the way down to 10%, we should get learning in 10 times fewer rewards, right? And so we're going to test this in the dopamine signal. And when we did that in the dopamine signal, we find that on a median, the number of rewards it takes the animals to actually show emergence of dopaminergic signal is actually about 10 times fewer than what it takes them with 100% probability. And just to show that this is actually a real signal, if you align the dopamine signal on this trial that we identified as where the dopamine learning is happening, it's clearly going up. And so this is just a cumulative sum of it. So a straight line here means constant signal. Right, so dopamine learning is actually happening 10 times faster in terms of number of rewards. Okay, so with that, I'm going to wrap up this part and say that if the total time is fixed, number of cue reward repetitions has 0 influence on overall learning, consistent with retrospective learning. So I'll very quickly give a taste of a second project. So this is to talk again about a project that Heejung has led and its implications for extinction. So extinction is learning that a cue that previously predicted an outcome no longer predicts the outcome. And extinction is important to understand for disorders such as addiction and PTSD. So for example, for addiction, it is a chronic relapsing disorder because long-term cue drug memories exist despite extinction or abstinence, right? And so what is the nature of this long-term memory is a key question in the field. So the quick thing that I'll just say is that this, if you take the idea of this retrospective association seriously, it actually provides a very simple explanation for this backward memory. So if you imagine that the cue predicts the reward 100% of the time, and that's what my daughter learned first, then both the forward and backward associations are 100%. But now if I show my daughter just the store a bunch of times but never give her the ice cream, the forward association goes down to 0%, but the backward association remains at 100%, right? Because it is conditional on rewards, and without getting rewards, you will not update it. So that means that retrospective association is a long-term memory of prior ice cream or drug use after extinction or abstinence. And so the hypothesis is that the original cue drug memory that remains after abstinence or extinction is of the retrospective association. And the corollary to this, which is not going to be a good treatment option, is that the only way to degrade this memory is to get the drug without the cue preceding it. And we've tested this, and I'm happy to talk about this in detail if anyone's interested. That I'll just acknowledge all the folks that did the work and funding sources, and leave you with this slide.